Hello guys, welcome back to my channel, and like most of the time, let's do another integral. So today we are going to do the integral I from 0 to infinity of sine to the sixth power of x divided by x to the sixth power dx. And if you've been watching my content recently, you will notice that this integral is extremely hard to do by standard techniques like Leibniz rule or uh, any other properties. I'm not going to name all of them, but all of the other methods that we know of integration. So if you've checked out my last two videos, you may notice that we've built up our arsenal when it comes to the Laplace transform. So without any doubt, I'm going to use one of the latest properties of Laplace transform that we've added in our arsenal. So let's review that property on a fresh page. See you there. So the property that we have to discuss is basically integral from 0 to infinity of a function of, in this case, t divided by t to the n dt is equal to 1 over n minus 1 factorial times the limit as s goes to 0 of the integral from s to infinity of the Laplace transform of the n minus 1th derivative of f of t with respect to s integrated. Basically, I'm talking about this property. We have to use this. There is no other way to actually simplify this further. Even if there is, it's really hard. So notice that in our case n is equal to 6, and our f of t is basically sine to the sixth power of t. Here, the we can call the variable t. You can write that as x again. Doesn't matter. So, in order to find an expression to basically evaluate this integral, we need to differentiate this f of t, r f of t, sine to the sixth power, n minus 1, which is 5 times. So it's going to be a lot of differential calculus in this video, more than integration, I'm afraid. But I mean, before we actually get to differentiating it 5 times, let me just write everything properly. So integral from 0 to infinity of sine to the sixth power of, say, t over t to the sixth power dt. I'm just changing variables from x to t, it doesn't matter, over n minus 1 is 5 factorial times, we can just write this applying the limit, integral from 0 to infinity of the Laplace transform of uh, differentiating f of t 5 times with respect to t ds. Again, Laplace transform with respect to s. So, to apply this nice property, we need to actually simplify this function, because first we need to take the derivative of this function 5 times. So it will be way better to work with a much more convenient form. So f of t is, notice, sine cubed of t, the whole thing squared, because 3 times 2 is 6. And sine cubed, we can just use the sine triple angle formula. Sine 3x is equal to 3 sine x minus 4 sine cubed x. So this means sine cubed x is nothing but 3 sine x minus sine of 3x all divided by 4. So let's go and plug that in here. So we have f of t is basically 3 times sine of x minus sine of 3 times x divided by 4, but the whole thing squared. We can take the 1 over 4, the whole thing squared outside is 1 over 16 times applying the expansion formula of this polynomial 9 sine squared x minus 6, 3 times 2 is 6 sine x times sine of 3x plus sine squared 3x. Now I want to use the double angle formula for the cosine to simplify this sine squared further. So now we have 9 over 2 times 1 minus cosine 2x in place of sine squared minus, I'm going to use 1 2 from the 6, so we just left with 3, and we have 2 times sine x times sine of 3x. And again the same identity of the double angle formula of cosine. So here we have 1 minus cosine of 2 times 3 is 6x over 2. So this is going to just be 9 over 32 minus 9 over 32 times cosine of 2x minus 3 times, we can use the product to sum formula to give us cosine of x minus 3x is negative 2x, but it doesn't matter if we have a negative, the cosine is an even function. So cosine of 2x minus cosine of x plus 3x is 4x. Plus half minus cosine of 6x over 2. One slight correction, this 16 was multiplied with everything, so we have over 16 like this, and 2 times 16 is 32, so we have 32 like that. I didn't just see the bracket there. So we have 9 plus 1 is 10 over 32 minus this 9 over 32 times cosine 2x minus this 3 over 16 times cosine of 2x, which is nothing but negative 15 over 32 of cosine of 2x plus 3 over 16 times cosine of 4x minus 1 over 32 times the cosine of 6x. This is basically the simplified expression for our f of, let's not call it t, f of x. Simplified expression for f of x. Now it's time to differentiate this expression 5 times. And this is way better to work with than this sine to the 6th power. So let's do that on a fresh page. Let's do differential calculus on a fresh page. See you there. So we have this expression for f of x. We have to differentiate this 5 times. Let's go on with the first derivative. Well, we can get rid of the constants, that's the best part, and then we end up with 2 times 5 over 32 is 5 over 16, and the derivative of the cosine will compensate for the negative and end up with sine of 2x minus 3 over 4 times sine of 4x and plus 3 over 16, because 6 over 32 is 3 over 16 times sine of 6x. Well, great. Second derivative of f of x is going to be, well, 15 over 8 times the cosine of 2x. I'm just applying the chain rule, differentiating the sine and then multiplying with the 2. Here with the 4, here with the 6. And minus 3 times the cosine of 4x plus 6 into 3 over 16 is reduced to 9 over 8 times cosine of 6x. Now it's time for the third derivative. This will be negative 15 over 4 times sine of 2x plus 12 because of the 4 now times sine of 4x minus 27 over 4 times the sine of 6x. And now the fourth derivative of f of x is negative 15 over 2 times the cosine of 2x plus 48 times the cosine of 4x minus 81 over 2 times cosine of 6x. And then finally the fifth derivative of f of x is going to be 15 times sine of 2x minus 192 times sine of 4x plus 243 times the sine of 6x. Fine, we end up with this expression. Now we can actually plug this back into our identity, our property. Basically I was 1 over 5 factorial times integral from 0 to infinity of the Laplace transform of the fifth derivative of, in this case, f of x ds. So whatever Laplace transform we take, we have to end up in a domain of S. And this is a 5, this is not an S. Fine. Taking the Laplace transform of this expression now that we obtained. Well, the Laplace transform of the sine of a times t is actually equal to a over s squared plus a squared. So we can use that here. So the Laplace transform of the fifth derivative of f of x is just going to be, well, we have this 15 and then this extra 2, so 30 over s squared plus 2 squared, which is 4, minus 192 times 4 is going to be 768 divided by s squared plus 4 squared, which is 16, plus 243 times 6 is 1458 divided by x squared plus 36. Fine, we have to integrate this basically with respect to s. So when we do that, we have 30 over 2 times the inverse tangent of s over 4 minus 768 divided by, well, 4 times the inverse tangent of s over 4 plus 1458 divided by 6 times the inverse tangent of s over 6. But all of that is still evaluated from 0 to infinity, definite integral, remember. So this is just 15. At 0, all of them will be going to 0 because inverse tangent of 0 is 0 collectively for all the terms. 0 over 4 is 0, 0 over, this is 2 actually, sorry for that. 0 over 2 is 0, 0 over 4 is 0, 0 over 6 is 0. So we just have 15 times inverse tangent of infinity over 2 is again infinity. So that will be pi over 2 minus, this will just reduce down to 192. And again, inverse tangent of infinity is pi over 2. This will again reduce down to 243 plus 243 times pi over 2 because of the inverse tangent. Now we can reduce this further to 33 pi over, so all of this actually reduces to 66 pi over 2, which is basically 33 pi. But that is just this integral part. Don't forget this 1 over 5 factorial. So I is nothing but 1 over 5 factorial times this integral that we calculated to be 33 pi. 5 factorial is 5 into 4 into 3 into 2 into 1, which is 120. So 33 pi over 120, which if you want to reduce is going to be 11 pi over 40. So that's an excellent integral, an excellent candidate for using this new Laplace transform, this more general Laplace transform property that I discussed in my last video. So please check my last video out if you don't know what I was talking about all this while when we introduced that identity. So let's draw a conclusion. So integral from 0 to infinity that we originally had of sine to the 6th power of x divided by x to the 6th power integrated with respect to x is in fact 11 pi over 40, using all our nice properties of Laplace transforms. And since this is an even function because it's raised to an even power, right? So any negative you have in both the numerator and denominator will basically just cancel out. So the integral from negative infinity to infinity of sine to the 6th of x divided by x to the 6th is nothing but 2 times I. So that will be 11 pi over 20. And that's a really neat result. The pi just comes in again and it's beautiful. So I hope you really enjoyed this video, guys, and you learned how to exactly apply the general Laplace transform property that I recently discussed. And please like, share, and subscribe to my channel. Recommend me to all your friends, mathophiles, mathematicians, anybody you know who's interested in this kind of stuff. I want to grow. You can follow me on Instagram. I have this username. And in the meantime, stay home, stay safe, have a great day, and peace out.